Hello. We're going to spend some time looking at Chapter 1, which is an introduction to matter and measurement. Just to start off, just to make sure that everybody's on the same page, chemistry is the study of matter and the changes that it undergoes. So in the back of our mind, we should always be thinking of the scientific method, which is the process that we take whenever we observe something and then look for patterns and then formulate and test hypotheses. So just have this in the back of your mind because we'll be spending a lot of time developing this thinking approach. First of all, what is matter? So matter, you should recall, is anything that has mass and takes up space. And when we envision matter, we think of it as everything is made up of these really small particles that we can't see. So what we want to be able to do is to represent those particles, because we want to be able to think about what's happening at that level and how it connects to what we do see. So I want you to pay close attention to these representations of various types of matter. So in the first case, you have an element. So you would show a representation, a particulate diagram with all the atoms being exactly the same. Then if you wanted to represent, say, a diatomic element, you would show, again, all identical but paired up 2 by 2 to represent that they exist as molecules. To show a compound that is molecular, you would want to show 2 different types of atoms combined together in a specific ratio. And then finally, to show a mixture, you would have to show that you have different types of particles, be it atoms, molecules, etc. So atoms, as you know, are the building blocks. Here are some examples of different molecules and how atoms can combine to form different molecules through covalent bonding. Each element is going to be made of the same kind of atom. A compound is going to be 2 or more different kinds of elements. I know it's cut off on the side. Then you have these states of matter, where we talk about how at different temperatures and pressures, matter can exist in a variety of states. So in the gaseous state, you have a lot of empty space between the particles. The particles have a tremendous amount of freedom, and they're relatively far apart. If that substance cools down, or if you increase the pressure, you can actually now have a liquid where you still have disorder, but now the particles are close to each other. And then finally, further cooling or increased pressure would produce a solid, where you have a specific arrangement. The particles are in fixed positions. They do have some motion, such as vibration, but they are very close together. Another way of classifying matter is in terms of its composition. So we think about the fact that matter can either be uniform throughout. If it's not uniform, it's a heterogeneous mixture, right? So that means you can see the different parts of the mixture if it's heterogeneous. If it is uniform throughout, then we refer to it as being homogeneous or homogeneous. Now, if it's homogeneous, is the composition vary? So you either have a solution, which is a homogeneous mixture, such as salt dissolved in water, right? You can't see where the salt particles are, where the water particles are, but it is still more than one type of particle. Or you have a pure substance. A pure substance means you only have one type of particle. And a pure substance is either an element or a compound. And that's just based on whether or not it can be chemically separated into simpler substances, then it must be a compound. If it cannot, then it must be an element. And as you already know, all the elements are on the periodic table, so you know exactly where to find those. Next, we looked at different types of properties. So a physical property is any property that you can observe without changing the identity of the substance, right? You can measure the boiling point. You can see what temperature it changes from liquid to gas. You can measure the mass, the volume, and the ratio of those things, which is density. You do not change the identity of that substance by measuring those properties. But then you have chemical properties, which are qualities that you can observe only if you change that substance. So if you want to see that something can burn, and you burn it, you no longer have the substance that you started with. So flammability then is a chemical property. The fact that it reacts with something, the fact that it corrodes, rust, etc. These properties are only observed through the process where it undergoes a chemical change and it becomes something else. So those are referred to as chemical properties. Another way of looking at properties are in terms of what we call intensive or extensive. An intensive property does not depend on how much you have. So, for example, the density of water is always the same. It doesn't matter if you have 10 milliliters of water or 100 milliliters of water, the density of water is still 1. Also, the boiling point of water. It doesn't matter how much water you have, the boiling point occurs at 100 degrees Celsius regardless of the quantity of water. An extensive property is one that depends on the amount. So that usually refers to some measurable quantity such as mass or volume, the amount of energy contained, etc. Similar to the types of properties, we have certain types of changes, and that's the physical change or the chemical change. So a physical change is a change in which the matter does not change its identity. So when something goes from liquid to solid to gas, its identity is still the same. So that would be considered a physical change. Chemical change, however, involves a change in the identity of the substance. So now you have a new substance. Burning, oxidation, any chemical reaction in which you form new substances, you would refer to those as chemical changes. Chemical reactions, which is another word for a chemical change, is where you have substances reacting to form new substances. So again, we want to pay close attention to the variety of representations. So here we would have the macroscopic view, which is what you can see, the tanks of hydrogen, the tanks of oxygen, and then the submicroscopic view, which is the particle diagram that would represent those substances combining to form water. Compounds can be broken down into elements, right? Just as elements can be combined to form compounds, the reverse is also true. Here you have an example of electrolysis, during which electricity is run through a sample of water, and that produces hydrogen and oxygen gases. I want you to reflect a bit on this section because this is going to be our first experiment on separating mixtures. The separation of mixtures can be accomplished using physical changes. So for example, if you have a homogeneous mixture or solution of salt water, you can separate them using a process called distillation. How does distillation work? Well, it takes advantage of the difference in boiling points of the two substances, because when the mixture is heated, only one substance is going to vaporize at a time. So whichever substance has the lowest boiling point will vaporize first, and you can condense that vapor and then collect that. The temperature of the mixture actually remains the same as long as that substance is in the mixture. Another process that you should be familiar with is called filtration, and this depends on the difference in particle size, because if a substance is not actually dissolved, then the particles are large enough that they will remain trapped in the filter paper, and just the solution, in this case it could be a solution or it could be a pure liquid, just the liquid will pass through, and whatever is dissolved in that liquid will pass through. So this can allow you to separate an undissolved solid from a mixture. Another technique that's important for you to recognize is chromatography. Chromatography relies on the difference in attraction between the components of a mixture with a moving medium and a stationary medium. So in this case, if we put a little bit of marker ink on a piece of paper and dipped it into some water, as the water moves up the paper through capillary action, you can see that the different chemicals that are in the ink are actually going to move up at different rates. And by using the ratio of the distance that they traveled, you can actually identify the compound itself. Very quick review of units of measurement. You should be familiar with the SI units. SI, which stands for System International. Those are the units that we use in science courses. We use a base unit for each quantity, and then we use the metric prefixes to allow us to adjust those quantities so that they're appropriate for what we're measuring. Please be familiar with the commonly used prefixes and their meanings. You will be required to know these. Also, just to be aware that 1 centimeter cubed is equivalent to 1 milliliter, and then 1,000 milliliters is equal to 1 liter, which is the same as 1 decimeter cubed. Those relationships are important. What about uncertainty in measurements? We have a variety of measuring devices that have different degrees of accuracy, and it's important for you to keep in mind how many digits you're allowed to record when you're taking a measurement. We're going to talk about which materials or which equipment is appropriate for which types of experiments as we go along, but just keep in mind that we want to be as accurate as possible. Temperature, as you know, there are 3 temperature scales. The one that you'll be using to measure is the Celsius scale, and for some purposes we would need to convert our unit from Celsius to Kelvin. So you need to be comfortable and confident with doing that as well. The Celsius scale and the Kelvin scale are most often used, and just for your information, the Celsius scale was created based on the properties of water. 0 was set as the freezing point of water, and 100 degrees was set as the boiling point of water. The SI unit for temperature is Kelvin, and we will need to use this unit when we're using the gas law, so keep that in mind. There are no negative degrees or temperatures in Kelvin. It's created as an absolute temperature scale, so the lowest possible temperature on the Kelvin scale is 0. In order to convert from Celsius to Kelvin, you will add 273.15 to your Celsius temperature. The Fahrenheit scale is not used for scientific measurement, but just for your own information, you can convert between the two. If you have a temperature in Celsius, you multiply by 9/5 and add 32. The reverse can be done to go the opposite way. Density, which is a physical property of a substance, you can solve for by taking the mass and dividing by the volume. What do we do to represent our uncertainty in measurements? We use something called significant figures. Just keep in mind that these are important. This dictates how many digits we can record in our answer. You should be familiar with these rules. If you have any questions, just let me know.